Hey everybody, welcome to week 3 of PS 231. Before we get into today's lecture, I just want to let you know, so this is the first video that I'm recording since the class got started. And I just wanted to let you know how pleased I am with how things have gone so far. And you're like, well, that's good, I'm glad there's one of us. So I just want to tell you how great I think that you're doing. Yes, you. I think the questions that I've seen on Piazza have been wonderful. I think the questions that you've been asking at our meetings have been wonderful. Sang-hoon tells me that the recitation was at least from his perspective, pretty good. It looks like you've been having at least some fun with some parts of your problem set, and you're like, well, fun's a strong word, and a point taken. But I just want to pause before we get started to say, there's a good chance that there have been moments of malaise, and there have probably been some times where you're like, I don't know what the heck this is all about, and that might be most of the time, but I want you to know that you can do it. And the people that I've seen in office hours or at the meetings, and this is not a trivial proportion of you, right? This is many of you. Even if you're not where you need to be, which is fine, you're at the beginning of your journey, you're doing a great job. I know that it doesn't feel that way. I know that you're all good students, right? You're smart. And you're used to things just immediate. But, some of this stuff isn't going to be so immediate. And that's okay. My job, among other things, and I don't know if I'm doing a good job of it so far, but I want you to know that what I view my job as is showing you things that are so cool that you think it's worth a few hours of feeling a little bit gross. I'm only asking for a couple hours of you feeling gross, and that's more than you get asked to feel sometimes, and I understand that, but it's worth it. If you ask me, those moments of grossness, now I'm asking you for a few hours, and Sang-hoon or any other professor could tell you that, when they're in grad school, those moments of grossness where they feel like they don't understand what's happening, those moments of confusion and malaise and isolation and fear, I can only speak for myself. Mine was 2 years. Mine was 3 years. I wouldn't recommend that, at least for your hairline's sake. But when you get it, when it clicks, and I know some of you have had some of this, I've seen it. I've seen in the big gallery view of Zoom, those little moments, those tiny little moments. That's as good as it gets, if you ask me. At least in terms of the brain part of your brain. My favorite thing in the world to do is to play with Chewy. His favorite game, he only plays one game. It's called Semi-Fetch-of-War. And that's my favorite thing. At least among things that I'm willing to talk to you about. I'm not going to tell you what my favorite movie is, or that notwithstanding, those little aha moments, those moments, embrace them. They're few and far between. Anyway, the subject of today's lecture is expected utility. It is the final foundational fable that you need before we can start talking about game theoretic fables. This is a class in game theory, but unfortunately there's a lot of stuff that you need to know in order to really be able to appreciate game theory for all its beauty. So in the previous lecture, we talked about 3 foundational fables of rationality, right? And so there was a set of alternatives, and we talked about 3 ways that we might evaluate a decision maker's evaluation. We, the analyst, evaluate the decision maker's evaluation. And we saw that there were 3 ways for us to evaluate that. There was the fable of rational preference relations, binary preference relations that are reflexive, complete, and transitive. The fable of utility maximization, the idea that you just assign every alternative some number, and that number represents something about, that number carries all of the ordinal information about how you rank the alternatives. So your favorite alternative gets the highest number, your next favorite gets the next highest number, and so on. And then we talked about this kind of weird, hairy idea of rational choice with this choice mapping and all these menus. You're never going to see that one again, all right? However, rational preferences and utility functions will come up a little bit more. In particular, this week is going to be when we construct our final fable about how people evaluate alternatives. So the previous lecture was about what happens if you have perfect agency over what you choose, right? So if you order a latte at Starbucks, you go to Starbucks and you order a latte, there was a finite set of alternatives of things that were available, although at Starbucks it feels increasingly like that's an infinite set, but there's a finite set of alternatives, cappuccino, latte, etc. You chose something, and if you went to a good Starbucks like the one in Urbana, then you actually get the thing that you ordered. With probability 1, it is a surefire bet that you will get what you ordered. Other Starbucks less so. Depends on whether they're on campus. But that isn't what happens in reality. In difficult, interdependent strategic situations, people don't just choose one thing and get exactly what they want. There's an element of uncertainty once matters get important and strategic. If things were certain, then it would be very easy for us to know what is best. We'll talk about that in a few weeks. But in the meantime, we have to think about how to make choices or how to evaluate alternatives where there's some element of risk involved, where there's some element of uncertainty, where you don't know for sure that when you order a latte, that you get a latte. So we need to talk about decision under uncertainty. And this gives rise to a very beautiful theory called the theory of expected utility. And so my goal for today is to give you a little pre-fresher in an expected utility. It's intuitive, and you're like, well, we'll see. What you think is intuitive isn't always intuitive, fat man. Point taken. But what I hope that you can see is that some of the muscles that you've been developing in the previous weeks are going to make you strong enough that these things are going to look a little bit easier as we go. What becomes intuitive to you is going to get harder and harder, right? There's beauty in getting stronger. So in the A block, I want to talk about the primitive of this model, which is a lottery. So instead of an alternative where you know for sure that when you order a mug of, well, this is hot honey lemon water to soothe my tiring voice, but when you order a cup of coffee, you get a cup of coffee for sure. That's an alternative. The primitive of our framework for today is going to be a lottery, where it's a set of outcomes, and you don't know which outcome you're going to get, but you do know the probability that you'll get any given outcome. So for example, if I say to you, I'm going to toss a coin, and if it's heads, then you give me $1, and if it's tails, then I give you $1, that's a lottery, right? There's probabilities involved. Whether or not that's a thing that you want to do depends on the coin, right? So the primitive of this model is going to be the lottery, and so I want to spend the A block making sure that we all know what a lottery is. It's a little bit complicated if you can start from something very simple, which is what we'll try to do, and then we'll come up with a more general way to think about these things. In the B block, I want to talk about preferences over lotteries. What would it be to like one lottery more than another lottery, right? So a decision maker has to make choices over uncertain outcomes. They have to choose one lottery over another lottery, right? When a leader of a country decides to start a war, there's some probability that their country will win the war, and there's some probability that their country will lose the war, right? They have to think about both of those contingencies, but they also must compare that war lottery, that sometimes I win, if it's heads I win, if it's tails I lose. They have to compare that lottery against the lottery of the status quo, where things might go great, things might go awfully. You don't know, right? You only have probabilistic expectations. And so now we have to think, hey, what's a decision maker? How are they evaluating different lotteries? Once they're in the world of lotteries, instead of in the world of alternatives, then we have to say, hey, how do they evaluate those things? And so that'll be the B block. What are preferences over lotteries? And then in the C block, I want to show you the simplest way the standard way for us to evaluate lotteries, right? So we're going to come up with a particular kind of utility function to assign to a lottery. It's called the expected utility function, or if we're being very fancy, the von Neumann and Morgenstern expected utility function. That just makes you sound cool at dinner parties, if we're being honest. And this expected utility function takes a very particular and intuitive form. Okay, so in the C block, things might suddenly make sense again. We'll see, give it time. Because we'll be talking about expected utility. So by the end of today's lecture, I'm hoping that you've taken some of these muscles that you've developed about what rationality is, and you're prepared to extend, you're prepared to go even further and say, hey, what is rationality when decision makers don't quite know what's going to happen based on their choices, which seems pretty realistic, right? So that's what we're going to do today. Let's get started. So here in the A block, we need to introduce the concept of a lottery. And in order to keep things super duper intuitive, I want us to think about monetary lotteries. We're going to think today is going to be a day measured in dollars, all right? At least the first two blocks, we're going to measure most of the things we're thinking about in terms of dollars and cents. It's something that will generalize to a little bit more broadly, and you'll see it's not everything we're going to see moving forward will be measured in dollars and cents, even though we keep using expected utility. But I think it's easiest to introduce these concepts through monetary lotteries. Let's suppose that we have some set of outcomes, some set of possible outcomes which are measured in dollars and cents, all right? And maybe you get $1, maybe you get $2, maybe you get minus $1, maybe you lose money. Maybe you get minus $10, but everything is going to be measured in dollars. And suppose that we've got a finite number of outcomes, a finite set of outcomes measured in dollars of what could happen. So for example, one element of that finite set might be you get $1,000. One element of that finite set might be you lose $1,000. You get a Google dollars, you lose a Googleplex dollars, and so on. To be explicit, that can include nothing, right? So it might be that you get no dollars. One option here is you get nothing, but some potentially. But so we have this finite set of outcomes, we'll call it X, just like before, but remember that every element of X is something that you get in dollars, okay? So if you had perfect agency over the elements of X, like we had last week, so you have a finite set of alternatives, right? And let's suppose that you have sort of the most sensible preferences over that. If you had perfect agency, if I offered you a finite set of alternatives, and it had like lose $1,000, zero, or get $1,000, it's not very interesting for me to try to model your choices, because you're just going to take the $1,000, right? We don't have to bring science into this. You like money, you like not losing money, you'll take the money. It's not very interesting. But the idea of a lottery is that what a lottery does is it says there's a certain probability that every outcome will happen, right? So for example, in that finite set of alternatives I just discussed, where you lose $1,000, you stay at the status quo, or you gain $1,000, right? What a lottery is a set of probabilities on those three outcomes. It's a set of numbers, all of which are positive, and they add up to 1, right? So for example, maybe you have a 20% chance of losing $1,000 in a particular lottery, okay? If that's the case, then maybe we'll say the probability that you lose $1,000 in that lottery is 0.2. And maybe you have a 50% chance of maintaining the status quo in this lottery. And so we would say the probability of you getting the zero outcome, the $0 outcome, is 0.5. So then maybe in this lottery, we know you have a 20% chance of losing $1,000 and a 50% chance of staying at the status quo. So that means that there's 30% left, right? They add up to 1. So that means that the probability of you winning $1,000 in this lottery that we're using for introductory example purposes is 0.3. Now I could have come up with different probabilities. So that was one lottery. Call that L1. There could have been different lotteries over that. Maybe in one lottery, you had an equal chance of all three outcomes. 1/3, 1/3, 1/3. Maybe in another lottery, you win $1,000 for sure. So it's 0, 0, 1. Maybe another lottery, you lose $1,000 for sure. So it's 1, 0, 0. Maybe there's another lottery where you never get $0, but you have a 50% chance of 1,000 or not 1,000, right? So it would be 0.5, 0, 0.5. So all I have is it's a vector. It's just a tuple. It's just one of these things where every element is a positive number, a non-negative number. Every number is greater than or equal to 0 and less than 1. And if you add them all up, you get 1. That's all that a lottery is a set of probabilities over some monetary outcomes. And you're like, that isn't what a lottery looks like to me. Au contraire, why don't we make a quick trip to the bookshelf of awesomeness? So I have something that might look like a lottery to you. So this is a lottery. It's a scratch ticket, right? This is from the mini mart. At the mini mart, this is the Illinois. It even has the word lottery on it. Do you see that? Illinois lottery. So the Illinois lottery sells for $1 this ticket, right? They sell this ticket for $1. And what all can happen? So it tells you on the front, of course, this is what they really want you to look at. They're like, oh, look, you could win $2,500 a month for 20 years. That's a pretty good payout, right? And there's certain things that have to happen in a scratch ticket like this, right? So we'll do this here eventually, but we don't know, as of right now, we don't know if this ticket will actually provide $2,500 a month for the next 20 years. We don't know that. Right now it's a mystery. What this is worth is a mystery to us. What do I mean a mystery? Well, I mean as of right now, there's a bunch of different monetary things that this thing could be worth. It could be worth nothing, right? So if I scratch off the scratchy part, and I get one of the combinations of icons that isn't a winner, right? Then this little piece of cardboardy paper is worth $0. Now I paid $1 for it, so that would stink. That would mean that I lost $1. But there are some other possibilities. I mean, so they even tell you on the back of these things, right? So they tell you, I don't know if you can see that. So they tell you, they give you approximate overall odds of winning. I'm going to convert these to probabilities just because they're easier. Okay? So the overall chances of winning, including break-even prizes, I'll give you a little bit more detailed lottery here, are 1 in 4.97, right? So you win roughly 1 time out of 5. You break even 1 time out of 5. So 80% of the time, this is worth 0. So I can put in probability 0.8. With probability 0.8, this gets me $0. Right? But there's other monetary outcomes that can happen, right? So you can see there's one option where you get $1 back, you basically win your money back. And the odds of you getting just your money back, the odds of this being sort of a net even for you, are 1 in 11.11. So I'm using a calculator here. So there's a 9% chance that you get $1 for this, right? So 0.09 approximately is the probability of this being worth $1 to you. The odds that you win $2, so the odds that you double your money, are 1 in 12.9. So the probability of you winning $2, of doubling your money with this, from going from $1 to $2, that's about a 7.8% chance. So then the probability that you get $2 out of this is 0.0775. The probability that you win $4, you have a chance of winning $4 with this. And the probability of you getting $4 is 1 in 8. It's 1 in 80 chances. So with probability 0.0125, right, you have a 1.25% chance of winning $4 from this lottery. You have a chance of winning $5 with this lottery. And this lottery will get you $5, 1 in 200, or a 0.5% chance. So you have a 0.5% chance of winning $5 with this lottery. So it's 0.005 probability. You could win $20 from this. This lottery could be worth $20 to you. Right now, these are all hypotheticals. We don't know. So your chances of winning $20 are 1 in 400. So you have a 0.25% chance. You have a 0.0025 probability of this getting you $40. This could be worth $100. This ticket could be worth $100. Okay? And the odds that you get $100 are 1 in 24,000. So now you have a 0.004% chance of winning $100 from this. So a 0.004% chance. That means the probability of getting $100 is 0.00004. You could win $1,000 with this. This ticket could be worth $1,000. This ticket could be worth $1,000. And the odds of that happening are 1 in 480,000. So you have a 0.0002% chance of winning $1,000 with this, right? So the probability of that happening is 0.000002. So there's a probability associated with this lottery of you winning $1,000. And finally, you could win $2,500 a month for the next 20 years, right? So it says so right here. And the probability of that happening, the odds of that happening, the chance that you do that, that's a 1 in 3.84 million. So you have a 0.00026% chance of winning $2,500 for the next 20 years with this lottery ticket. So again, that's the probability of that happening is 0.0000026. So this is a lottery. This is a lottery both in name. Am I pointing to the right part? No. This is a lottery in name, but it's also a mathematical lottery, right? It's a set of probabilities over a finite set of monetary outcomes. So presumably many of these were printed. I'm guessing that only one person is going to win, right? But there's many of these tickets that got printed, but only one of them, I'm assuming, is the one that has $2,500 a month for the next 20 years. I'm assuming that. So the value of this is, I paid $1 for this, even though I don't know what it is. I gave away $1. I gave away, let's compare. I'll be right back. Here's $1. That's what, if you want this lottery, you have to give up $1. Now, with probability 1, this is worth $1. This is a lottery too. It's just a very boring lottery. Exciting lottery, boring lottery. Chance of many different things happening, chance of one thing happening. Okay? So the idea here is that this was worth $1 to somebody. In particular, it was worth $1 to me. I don't buy lottery tickets very often, but right? When people buy these all the time. People go to the store, the mini mart, whatever. They go to the mini mart and they spend $1 on this, even though they don't know what it's worth. Right? They don't know for sure. They don't know for sure what's going to happen. And of course, there were many different things that they could have bought. Right? There's all sorts of lotteries. They had to choose a lottery. They went into the mini mart and instead of choosing between Coke, Pepsi, and Sprite, like they did last week, now they went to the counter and they said, oh, I need to evaluate these lotteries. How do you do that? This is a lottery. These are lotteries. Lotteries are just probabilities over monetary outcomes. In today's lecture, we'll generalize that to it can be over many different outcomes. But right now, let's just only think about money. Yeah, my mind on money and my money is also on my mind. So this is a lottery. And the idea is that there's a set of lotteries, right? Instead of there being a finite set of outcomes, like we had last week, Coke, Pepsi, and Sprite, the basic idea here is that there's going to be a set of lotteries where, sometimes the numbers in question are the same. So you can win $1 with this and you can win $1 with this. They offer you different probabilities of winning $1. So even though these tickets cost the same, the odds of winning $1 with this lottery ticket are 1 in 11.11, and the odds of winning $1 with this lottery ticket are 1 in 10.53. Right? So different lotteries give different probabilities, even though these were both worth $1. This one, the highest possibility is just $3,000. And this one, the possibility is $2,500 a month for life. So this is worth, the high end of this is worth a lot more, right? So the most that you could win with this, right? They can give you an annuity. You can get an annuity. So you can either take this gets even. So you can either get $600,000 in annual payments for $30,000, or you can win $360,000 immediately. They can just give you $360,000 now. So you can have $600,000 over time, or $360,000 now. This one doesn't offer you anything close to that. The highest number for this is 3,000. So there are numbers that this one hits. There are outcomes that this one hits that this one doesn't. And this one you can win 3,000. That wasn't a possibility on this one. So different lotteries might have different possible outcomes and different probabilities over those outcomes. Okay? But that's all that a lottery is. Now I think one nice way to draw finite lotteries like these, where there's a finite number of alternatives, okay? A nice way to draw that is with these little trees. Okay? So if there's 4 outcomes maybe draw that with 4 branches on a tree. And with probability, let's just do hypothetical, maybe there's a lottery over those 4 outcomes. Maybe the outcomes are win 2, win 1, 0, and lose 1. Okay, so there's 4 outcomes. And maybe the probabilities of that are 0.1, 0.2, 0.3, and 0.4. So I can just put a little probability number on each branch of the tree to tell you. And now you've got both the outcome possibilities. So 10% of the time you're on that north track, and that takes you to $2. 40% of the time you're on the south track, and that takes you to minus $1. Okay? So these little trees are really convenient. These trees are a nice way for us to summarize, for us to visualize what's going on in a given lottery. Now with really complicated lotteries, you're not going to be able to draw them all, but you're not going to have to do really complicated lotteries. Some of these are very complicated. I mean, so this is just a matter of scratching, right? So here you just scratch, and you just need to match numbers. So there's one number here that's the winning number, and all you have to do, you get 5 chances. You get 5 chances to match this number with these. So in fact, I'm just going to scratch this, okay? This will no longer be worth $1. Well, there's a chance it'll be worth $1. There's a 1 in 11.11 chance that it's worth $1. But odds are this will not be worth $1. Any proceeds that I get will be donated back to the university. So the way that this lottery works is I need to match this winning number. So my winning number is 15. Right? So if I get a number that matches, and we're going to see if any of my scratch numbers match 15. And they don't.
Loser!
Right? So this lottery, I had to get a 15, and the numbers that I got were 19, 10, 4, 5, and 3. So none of these match. So now that I have scratched this ticket, it is worth $0. There is no longer anything probabilistic happening, right? Before I scratched that ticket, there were hypothetical possibilities that ranged from nothing, which is what happened, to $360,000. So I got excited. Even when I was scratching this ticket, part of me, some tiny part of me was saying, oh man, I've got a 1 in 3.8 million chance of winning $360,000. But it didn't happen. There's nothing probabilistic about this. This is worthless piece of paper, right? So now compare this piece of paper with this piece of paper. Which piece of paper? I'll take this one, thank you. This one is linen, actually. So that's the concept of a lottery, okay? All that a lottery is a set of probabilities over some set of monetary outcomes. $1, $2, lose $1, lose $10, whatever, okay? I can also have a compound lottery. What the heck is a compound lottery? It's a lottery over lotteries. So, here's the lottery. This is the other one I was talking about before, the 7-11-21 game. So this game, I could win nothing. I could win 1, I could win 2, 4, 5, 10, 25, 30. I could win $50, I could win $100, or I could win $200 or I can win $3,000, right? So I can win all these. This is a hypothetical again, right? This is a lottery. And here's another lottery. This lottery somebody paid $2 for. This lottery is only worth $1. So what does it mean for you to be willing to pay more for this one than this one? Is it because you think cupcakes are pretty? No! I mean, cupcakes are pretty and delicious. Probably not this one. That purple looks kind of gross. Right? But why is this lottery worth more in dollars than this lottery? Why did somebody pay more for this one than for this one? Well, it's probably because there are better probabilities on higher numbers on this one than there are on this one. It's not the cupcakes. And none of these are fun games to play. I hate scratching. I don't want to do this. This is annoying. Okay? Nevertheless, somebody paid more. So what's a compound lottery? A compound lottery is a lottery over lotteries. So here's a lottery. In this lottery, you have a certain set of probabilities, and I'll put the probabilities over the screen of the certain outcomes. Okay, so it's just a vector of probabilities over those numeric, it's just a vector of probabilities over those monetary outcomes. Okay? And this is also a lottery, right? This is also a set of probabilities over some set of monetary outcomes. And I'll put that on the screen. So we've got 7-11-21 lottery, and we've got cupcake cash lottery. For this you're paying. So it could be that you just play this lottery, which right now is a set of probabilities. It's a decision tree, right? It's a tree. It's just a tree with all these probabilities. And this is just a tree with all these probabilities, right? Those are two simple lotteries. These are simple lotteries because all it is a set of probabilities over the outcomes. Great. What's a compound lottery? Well, a compound lottery goes like this. Here's the penny. I use this penny to scratch these tickets, or that ticket that I scratched. I use this penny. Okay? So this penny I can use to create a compound lottery over these two lotteries. So suppose that it wasn't just a matter of these. Suppose that I said, I'm going to toss this coin. I love that I'm stroking my beard like tossing coins is profound. Oh, just imagine if I tossed a coin. And you're like, provocative. So I toss the coin. And if it comes up heads, then you get to play 7-11-21. If it comes up tails, you get to play cupcake cash. That's a compound lottery. It's a lottery over lotteries. What I'm saying essentially is, assuming this is a fair coin, you have a 0.5 chance of getting this set of probabilities, and you have a 0.5 chance of getting this set of probabilities. It's a lottery over lotteries. And nothing stopped me. It could have been more than 2, right? So I've still got 4 tickets left that I haven't scratched. So I could have said that you have a 25% chance of playing 7-11-21. I could have said that you have a 25% chance of playing cupcake cash. I could have said that you have a 25% chance of playing The End of Alzheimer's Begins With Me. It's a weird name for a lottery. I wish it was true. I mean, it's a wonderful sentiment. But I don't know if that's what I would name my lottery. And a 25% chance of playing $50,000 crossword bonus. Right, so I could have had 4 lotteries that I randomized over, and it didn't have to be an even chance. It could have been 90% chance that you play 7-11-21 and whatever. So that's just a set of probabilities over lotteries, instead of a set of probabilities over the monetary outcomes themselves. Okay? Now let me go back to a simple example to show you that a compound lottery is still a lottery. Okay? So suppose there were 2 monetary outcomes. You win $1 and you lose $1. Okay? And suppose that in lottery 1, you had a 70% chance of winning $1 and a 30% chance of losing $1. Okay? And suppose in lottery 2, you had a 60% chance of losing $1 and a 40% chance of winning $1. So those are 2 lotteries. They're just sets of probabilities over a well-specified set of monetary outcomes. But suppose then that I said, I'm going to toss a coin. I'm going to toss a coin. And if it comes up heads, then you play that first lottery, that 70-30 lottery. And if it comes up tails, then you play the second lottery, which was that, 40-60 lottery. Okay? So now we've got a compound lottery. There's like a first part of the tree that tells you, hey, are we in the heads world or the tails world? And we know the probabilities of those happening because it's a fair coin, we'll say. And then if it's heads, we play one lottery. And if it's tails, we play another lottery. And so remember, that means that you have a 50% chance of having a 70% chance of winning $1. And you have a 50% chance of having a 40% chance of winning $1. So in other words, we can come up with the probability of winning $1. Well, it's 0.5 times 0.7, that's 0.35, plus 0.5 times 0.4, that's 0.2. So in other words, if you played the lottery, toss a coin, and if it comes up heads, play the one lottery, and if it comes up tails, play the other lottery, then in that compound lottery, your chance of winning $1 is 55%. You have a 55% chance of winning $1 in that world that I just described. Probability of 0.55. Now, in order for this to be a lottery, then it's got to be that we've got numbers that are positive and add up to 1. So an interesting question is, do you also have a 45% chance of losing $1 in this world? Well, let's think about that. So with 50% of the time, you have a 30% chance of losing $1. So that's 0.15. That's just 0.5 times 0.3 is 0.15. And then 50% of the time you're in the tails world. And that means that you have a 60% chance of losing $1. So 0.5 times 0.6 is 0.3. And lo and behold, that gives you a 45% chance of losing $1. So this lottery, which was in 2 steps, I toss a coin and then we play a lottery, right? Depending on how the coin turned out. That was exactly the same lottery as if I had just had a lottery that was you win with probability 0.55 and you lose with probability 0.45. So a compound lottery is still just a lottery. And this is going to be what we think the decision maker is evaluating. We think, oh, well, there's this world of lotteries. There's a set of outcomes, which right now we're thinking about in terms of money. So there's a set of outcomes, and over that set of outcomes, there are different ways to assign probabilities to those outcomes. Some of them are simple one-step procedures. Those are just basic introductory lotteries. Just a lottery, just a simple, straightforward lottery. But there might be multi-step procedures that get you from where you are to the outcome that you're destined to have, right? There might be a compound lottery. It might be that you make one step, and then with probability with one probability you're in one world, another probability you're in another world, and then you make another choice, and then you make another risky, right? Something probabilistic kind of keeps happening until eventually you find yourself at wherever you're going to wind up. Okay, so that's the building block of this model. This is instead of an alternative, now we're going to be evaluating lotteries, be they simple or compound. All right? Now this is realistic. You go into the world, you make any decision of any importance. Any decision of any importance that's like where there are stakes involved or where there's competition happening or something like that. You make any choice. Chances are excellent that you don't know for sure what's going to happen. If you start a war, you don't know you're going to win it. When you launch a political campaign, you don't know you're going to win it. You don't know. You only have probabilistic expectations. You buy a stock. You don't know if it's going to go up or down or stay the same for sure. You only have probabilistic expectations. And what determines the price of that stock? What determines the price of a lottery ticket? The likelihood that people think that there are of it going up, it going down, or staying the same, and also how much that is. So life is full of lotteries. A lot of the choices that you make in your life moving forward, just remember this, a lot of the choices that you make moving forward, this isn't game theory anymore. I'm talking to you personally. As a grizzled old person talking to you, a young person, who thinks everything is certain. You think you're going to make a choice and you're going to get it. Well, this grizzled old jerk is here to tell you that that ain't true. And you have to be ready for that. You have to think, hey, what's a good way? What's a consistent way to make choices amid all of this uncertainty? And the people that live in our fake mathematical fable world, they have to make those kind of choices too. So what's a reasonable way for them to make choices? We need to talk about preferences over these lotteries. Let's go to the B block. All right, so we define the concept of a lottery. A lottery is just a set of probabilities over some set of outcomes, okay? At the end of the last block, we said, well, how are we supposed to evaluate maybe even like a surefire dollar versus, so this is a lottery that assigns probability 0 to every monetary outcome except for 1, which it gives a 1. So with probability 1, this is worth $1. This is a lottery. You might call it a degenerate lottery, in the sense that all of the probabilities are 0 except for the 1. This is now a degenerate lottery as well. The scratched ticket, this is a degenerate lottery. This is worth $0 for sure, right? So with probability 0.1, this is worth $0. That wasn't the case before I scratched it. But let's say that we have a finite set of lotteries. So let's say that we have 5 lotteries, okay? So I have an unscratched version of that ticket from my other class. So here's one. There's 5 alternatives. The 20 years of cash lottery. There's the 7-11-21. There's the cupcake cash. There's the end of Alzheimer's. And there's the crossword one. All right? There's 5 lotteries. So suppose that I have 5 lotteries. And I want to view these like they're Coke, Pepsi, Sprite, Diet A&W, and Latte. Right? So I want to draw a doodle. I want to come up with a preference doodle over these. That's what we're talking about today, is preference doodles over these. Okay? So, suppose that we have some set of these, like there's 5. I've got 5 lotteries, or whatever, okay? And I need to come up with a doodle. And I'm gonna make assumptions about what the doodle has to look like. All right? So I just want you, this is gonna be a very short block, and the reason it's gonna be very short is I just want you to think about lotteries, vectors of probabilities, as the inputs of a decision model. Okay? So we want to be thinking, hey, what are people's preferences over these things? So let's just draw them out. So I'm just gonna draw out. I need 5 dots, right? I need 5 dots. So one of these is the cupcake. One of these is the 7-11-21. One of these is the 20 years. One of these is the crossword. And one of these is the end of Alzheimer's. And suppose I look at these. So I'm the one person that looks at the back of the lottery ticket to see what the probabilities are. And I evaluate the probabilities. Now I'm thinking. So I'm looking through, I'm thinking, I'm evaluating these lottery tickets. And I'm thinking to myself, well, I like each of these at least as much as itself. If you offered me 2 identical, right? I'm indifferent between 2 identical crossword lottery tickets. I have reflexive preferences over these. For any kind of lottery, I like each lottery at least as much as I like it itself. I'm talking incredulously because that's obvious. I like this as much as I like this. It's just like Diet A&W. So I have reflexive preferences. I can draw swirly arrows on each of my 5 dots. And I'm actually going to assume that my preferences over lotteries satisfy all 3 of the rationality postulates from last time. So I'm going to assume that I have reflexive, complete, and transitive preferences over these lottery tickets. Now, that might be a bit much to ask because I actually have to go to the back and look at them. It could be that I happen to come up with reflexive, complete, and transitive preferences that are just based on how pretty that I think they are. I love purple, and then I love cupcakes, and then I love crosswords, and then I love 7-11-21 because I actually like to play blackjack, and then I like 20 years of cash. So maybe my preferences are just based on prettiness. Or maybe I actually go to the back and I look and I say, oh, and I get my calculator and I say, oh, oh, this one gives me a 1 in 11 point chance of winning $1. This one gives me a 1 in 10.53% chance. This one gives me a 0% chance of winning $1. This one gives me a 0% chance of winning $1. This one gives me a 0% chance of winning $1. These were all more expensive than $1, so they wouldn't just give you $1. You either, if you're a loser, they don't want you to come back and say, hey, could I just have some change?
Loser.
So I'm gonna draw some doodles. Let's say that I'm indifferent. I'm just gonna say, I'm guessing that I'm roughly indifferent between the $3 ones. So the end of Alzheimer's and the crossword clues, they were both worth $3. So I'm probably indifferent between those two, and I like them both more than cupcakes. And I like cupcakes more than 7, 11, 21 in the 20 years. So I can come up with I'll draw it. I mean, I don't want to draw it here on my whiteboard. I can draw a complete reflexive transitive doodle over the 5 dots that I have in my hand right here. I'm going to informally describe 2 more criteria that I can't draw quite as well. I just want to say that there are 2 other criteria, all right? And the idea is like this. The first one of these is called continuity. And the idea of continuity of preferences is the following. So suppose that I like the crossword lottery more than I like the cupcake lottery. So suppose that my preference is suppose I have a strict preference of this lottery over this lottery. Okay? Then it has to be the case. It should be true that if you took this lottery, which is a set of probabilities, I'll write the probabilities on the screen. So this is a set of probabilities, and this is a set of probabilities. And I like this set of probabilities more than I like this set of probabilities. It has to be true, according to the continuity assumption, that if I like this strictly more than this, then there's some little adjustment to the probabilities, some teeny tiny adjustment to the probabilities. There's an adjustment to these probabilities that's small enough. I could just I could perturb them a little bit. Right? Instead of having the odds of 1 in 7.69 of winning $3, as I currently have in this lottery, maybe I have a 1 in 7.68% chance, 1 in 7.68 odds. Right? I could change this lottery a little bit just by switching those probabilities just a tiny, tiny bit. And the idea of continuity is the following. If I strictly like this more than this, then it must also be true that if I tweak this one a tiny, tiny bit, I have to like that more than I like this. There's some amount of tiny tweaking. There's an amount of tweaking so tiny. There is sufficiently tiny tweaking. Tiny, tiny tweaking. There is a sufficiently tiny amount of tiny tweaking that I can do and still like this strictly more than I like this. That's the idea of continuity. If you like this more than this, then you have to like a tiny perturbation of this as much as this. You're not going to see that again. I just wanted to mention. I'm just going to mention all 4 of these. Okay? So I'm assuming also that my preferences over lottery satisfy that criterion. That makes sense. Right? I actually think that that's the most sensible of the 4 so far. Oh no, reflexiveness is good. But other than, I think that probably the second most plausible thing I've mentioned to you so far is this continuity requirement. Right? So reflexiveness is very good. Reflexiveness is very intuitive because I want to like crossword as much as crossword. I want to like cupcake as much as cupcake. But I would say the second most plausible thing, that if it were true that I knew that I liked this more than I liked this, then I would also want to know that I like something really close to this more than I like this. Okay? And that's my requirement right now. So right now we've made 4 assumptions. We've assumed that we have preferences over these lotteries that are reflexive, complete, transitive, and satisfy this continuity requirement. They're continuous. Okay? And there's one 4th one, and it's the most controversial one. And it's something that if you ask me questions like at office hours, or if you email me next semester, if you email me sometime outside of class and say, hey, I want to talk about this, I'll talk about this all day with you, but I just don't want to talk about it too much today. But the controversial assumption that gets made about preferences over lotteries, and you're like, why are we making more assumptions? I get to have utility functions. You'll see. Okay? I'm making more assumptions because I want to get something stronger than just a utility function. Right? We said that reflexive, complete, and transitive was enough to have a utility function. But I want more than a utility function. I want something easier to use even than a regular utility function. You'll see what I mean. So I'm making stronger assumptions because I want a stronger result. Right? If I'm willing to make more assumptions, then I get to have cooler toys to play with. Fewer assumptions, less bling bling. Mathematical bling bling, not gambling bling bling. So the fourth assumption that gets made is the following. So suppose that I told you that I like this lottery more than I like this lottery strictly. Okay? I have a strict preference relation. This is as good as this, and this is not as good as this. Right? I have a strict preference relation. So suppose that you knew that. Now, this independence axiom is going to ask for a bigger promise. It's going to say that if you knew that that was true, then you also have to know that some mix of this and of crossword and a third lottery, which I should put right side up, let's say it was 80-20. If I like this more than this, then I have to like an 80-20 mix of this over an 80-20 mix of this. Okay, for any mix, 50-50, 80-20, 20-80, for any mix, all that matters is it's the same lottery. So a mix of the crossword lottery and the 7-11-21 lottery has to be better than a mix of the cupcake lottery and the 7-11-21 lottery. These are the same lottery. Okay, so the idea is that if you knew that this one beat this one, then something that is like the average of this one and something else has got to be the same, has got to still be better than the average of this one and something else. Okay? That's all. That's the independence axiom. It is incredibly controversial. It is not a good description of how humans actually make decisions under uncertainty. Which is to say, as a positive theory, this is a little bit off. This is not a good describer of how people actually make choices. If you put them in a laboratory and say, hey, which of these do you like more? Huh? Nevertheless, it makes things very simple. And you're gonna see how simple here in a second. But that's all that's happening right now. So we've made 5 assumptions. We have 5 assumptions about our doodle. Okay? And those assumptions are the following. Our doodle is reflexive. Every lottery is at least as good as itself. Our doodle is complete. For any pair of lotteries, you either like one more than the other or you're indifferent. You can't say I don't know about any 2 lotteries, which if you go to a casino, a lot of people look like they don't quite know which one they want to play. Transitive. If I like this lottery more than this lottery, and this lottery more than this lottery, then I have to like this lottery more than this lottery. A more than B, B more than C, then A more than C. So that's all from last week. I just added 2 more requirements. The fourth assumption is continuity, which is to say that if I like, I don't know, the cupcake lottery over the 7-11-21 lottery, suppose that you knew, this is a promise, if you knew that I like this more than this, if you knew that, then you should also get to know that some tiny change of this, some small perturbation, some lottery that's very close to this one, is better than this. So the idea is that small perturbations don't change your preferences. And then finally, the independence axiom. And the independence assumption says that if you knew that I like the crossword lottery more than the cupcake lottery, right? Then you should also get to know that I like some mix of these 2 lotteries, crossword and 7-11-21, more than I like these 2 lotteries, cupcake and 7-11-21. So that's 5 assumptions. Reflexive, complete, transitive, continuous, and independent. Those 5 assumptions, we already had enough to define a utility function over these lotteries. Right? We knew that reflexive, complete, and transitive was sufficient for a utility representation, right? So the question is, why the heck are we making more assumptions? I'm going to tell you why in the C block. So I want to introduce an important concept. I want to introduce sort of, if you were a statistician, how would a statistician a person that does statistics, somebody well versed in probability and statistics, how would they evaluate one of these lotteries? Well, that's a good question. So they would look at a lottery and they would see all the probabilities and all the outcomes, right? And they would say, well, with 1 in 11 chances, so with probability 0.09, you have like a 9% chance of winning $1. And you have a 1 in 12.9 chance of winning $2, and a 1 in 80% chance of winning $4, and a 1 in 200 chance of winning $5, 1 in 80 chance of winning $10, and a 1 in 400 chance of winning $20, and a 1 in 800 chance of winning $40, and a 1 in 24,000 chance of winning $100, a 1 in 480,000 chance of winning $1,000, and a 1 in 3.8 million chance of winning $600,000, depending on how you wanted to do it, right? So this lottery is a set of probabilities over the set of outcomes. And the question is, what is it worth? Now, we've been talking about subjective utility, how I value these things. But there are objective indicators that I might use to try to get a sense about what this is worth. One thing that I might do is I might take all those probabilities and all those outcomes and try to say in dollars what I think this is worth in expectation. What's the expected value of this in dollars, right? So let's work that out. Let's work out how much this lottery ticket is worth. So if I take all these probabilities and I add them, implicitly there's a probability of getting $0, right? So 0.09, because that's going to come up short, plus 0.0775 plus 0.0125 plus 0.005 plus 0.0125 plus 0.0025 plus 0.00125 plus 0.00004 plus 0.00002 plus 0.000026. The probability of winning something in this lottery is about 20%. That's what it promised you. It said that you had like a 1 in 5 chance of winning something. Well, that means you have like an 80% chance of not. So your probability of getting a 0 is 0.8. I have my computer open because I'm gonna have to do more calculations and I'm starting to get carpal tunnel. Why am I talking like this all day today? Okay. So if I want to know the expected value of this, I would just take every probability and multiply it by the number that you get. I would take a weighted average. I would use these probabilities to make a weighted average. I'd say I have a 9% chance of winning $1, 0.09 times 1. I have a 7.75% chance of winning $2, 0.0775 times 2, and then add them up. Right? And that'll get me something that's measured in dollars, not in probability, right? So I'm getting on my spreadsheet, I'm getting all of these numbers lined up so that I can just flash them on the screen very elegantly. And you're like, how did he come up with those numbers? Well, I made a spreadsheet like anybody else would, but the beauty of television is I can edit all that out. So when you work it all out, you take every probability and you multiply it by the dollar amount that probability gets you to. You end up with what's called the expected value of this lottery. And the expected value of this lottery ticket which cost $1 to buy, this lottery ticket cost $1 to buy, right? But it's only worth an expectation, it's only worth 65 cents. I'll repeat that. The expected value, when you work out the expected value of this lottery ticket, the probability of every outcome times the amount of money in that outcome, This lottery ticket is worth 65 cents, and it cost $1 to buy it. Now, does that mean that I'm not rational? No. Maybe I really enjoy, maybe it's worth 35 cents to me to get a little bit of action, right? This is how gamblers feel. Gamblers enjoy the action. That's why they have the term for that. So they're willing to make what might look like a bad purchase because they're risk acceptant. So here's something that in expectation is worth 65 cents. I was willing to pay $1 for it. That makes me risk acceptant. I'm willing to pay more than this thing is worth because I enjoy the action. I'm risk acceptant. I'm willing to take on that risk because, to be honest with you, Chewy's college fund is not where it needs to be. I would love a chance to win 20 years of cash. Right? I mean, I know he's not a smart dog, but he's still going to get into some good private school, and he's not going to want to go to a public school because I work at a public school, and so he's going to separate himself from dad. That's how it goes. Suppose that you weren't as silly as me. Suppose that you weren't as risk acceptant as me. Suppose that you, a smart person, and I'm a smart person, right? I was willing to pay $1 for this because I'm risk acceptant. Suppose that because this thing is only worth 65 cents in expectation, suppose that you were only willing to pay 65 cents for it. If it cost 66 cents to buy it, you wouldn't do it. If it cost 64, you'd buy it and feel like you saved a penny. Okay? So suppose that you were indifferent between this thing and 65 cents for sure. Suppose that you were indifferent between those two things. Then I would say that you are risk neutral. And a risk neutral person is the person that in expectation does the best. They maximize their expected value. They always choose the thing that maximizes their expected value. I gave up $1 for sure, which has an expected value of $1. I gave up $1 for this. So what I did technically wasn't best in terms of expected value. But I was willing to take on the risk because Chewy needs to pay for his college. Right? So that's the idea here. You're risk neutral if you are indifferent between the expected value of this thing and that amount of money for sure. Now suppose that you wouldn't even be willing to pay 65 cents for this. Suppose that you were like, 65 cents could buy me an entire feast at Taco Bell. Right? If you weren't willing to pay 65 cents for this, you would be what's called risk averse. Okay? This plays a big role in game theory and certain parts of political science, like in international relations when you're starting a war, most of the time we assume that you're risk averse. You don't just start wars for no reason. You don't say, oh, I think I'm probably going to lose this war, but I like the action. There may have been a time when that happened, like when kings were starting the wars and not fighting them, although I guess it's a little bit naive to say that isn't the case now. Right, but if you weren't willing, if you thought that 20 cents for sure was still better than this, then you'd be risk averse and that would be fine too. So that's risk neutrality, risk aversion, and risk acceptance. And this expected value plays a really big role in knowing whether you're risk averse, risk neutral, or risk acceptant. Right? If you'd rather have the sure thing, then you're risk averse. If you'd rather have a little bit of I'd be willing to pay. Maybe I'd even be willing to pay $2 for this. I'm very risk acceptant. Okay? That's all that's going on there. And that expected value played a really big role in defining what I meant by risk averse, risk neutral, and risk acceptant. If I didn't know the expected value, then I wouldn't have been able to figure out if I was risk acceptant or risk neutral or risk averse. So this expected value plays a pretty big role, right? This expected value is a very important thing. This expected value, this probability of an outcome times the money that you get for that outcome, or the utility that you get for that outcome, right? Suppose that you have utilities over all the outcomes. Instead of just numeric dollars, suppose that you're allowed to have different, maybe $1 means more to you than it does to me. Okay. Regardless, this expected value is a very important tool, right? Here's a result. If my preferences over these lotteries satisfy reflexiveness, completeness, transitivity, continuity, and independence, the things we talked about in the B block, right? That is true if and only if the expected value is my utility function over the set of all lotteries. So in other words, expected utility is a way to proceed if and only if you satisfy those 5 requirements. This tool that everybody uses, right? Even if you don't look at the back of the lottery, if I just gave you a problem set that said, hey, here's a lottery ticket, and you'd be like, hey, thanks, I'm dropping the class. If I said, hey, here's a lottery ticket, tell me what the expected value of it is. Eventually, you'd turn over to the back and start thinking about the probabilities. That's just a natural thing to do, right? If I said, how much would you be willing to pay for this? You wouldn't just look at the color palette. You'd switch to the probabilities. You might even calculate the expected utility, the expected value, right? So what we're saying here is that expected value technique, that simple, straightforward Microsoft Excel technique, 3 columns in Microsoft Excel, that's the way to go if and only if you had a preference relation that satisfied those 5 criteria. So whenever you do that little calculation, implicitly you're saying, I'm behaving as if I had preferences over lotteries that satisfied those 5 criteria. That's pretty cool. That's a very famous result due to von Neumann and Morgenstern, who published this in their 1944 treatise, The Beginning of Game Theory, Theory of Games and Economic Behavior. It's a huge deal. You understand it because this is... And so the idea here is that you get more than just a utility function, which is a very simple tool. You get the easiest utility function there is to work with, which is just make a Microsoft Excel spreadsheet over the outcomes with the probabilities. That's easy. Anybody could do. You're going to do that on your problem set. You're going to calculate some expected utilities, and it's not going to take you very long. That's going to be the warm-up of your problem set. And I'm saying to you that if you do that, if that's your mechanism, if that's your algorithm for finding what your favorite lottery is out of a bunch of lotteries, then you're behaving as if you had not just rational preferences over those lotteries. You're behaving as if you have very rational and continuous and independent. So that's what expected value, expected utility is all about, is assigning every outcome a number, right? Whether it's $1 or 3 utility points. And then taking every outcome, multiplying the utility, the value from that outcome, by the probability in question for that outcome, and adding them up. That's pretty cool. So on your problem set, I'm actually going to ask you to work out 2 very famous expected utilities that play a key role in 2 different literatures in political science. One is the calculus of voting. What is the expected utility of going to vote? And the other is the expected utility of starting a war. And both of them are super simple and straightforward. It's going to get easier. We had to do all this legwork to see when we get to do easy things. But expected value, expected utility, you can do this. And now you know why. So expected utility takes what we learned about utility last week and extends it to allow for uncertain outcomes, which is good because there's all sorts of things in life where, whether because of true uncertainty or uncertainty about others' actions, you don't know what's going to happen. What do I mean by that? Well, on the uncertainty side, suppose that you have a headache and you want to know whether or not you should take an aspirin to make the headache go away. Okay. You might measure whether or not that was a successful thing by how long your headache lasted after you took the aspirin. Now, it's silly for you to think that you know exactly how long your headache will last, conditional on you deciding to take an aspirin to try to remedy it. You don't know that. You might have some probabilistic expectations. You know that your headache won't go away in 0 seconds because the aspirin will take some time to kick in. And you know it won't take 1,000,000 years for the aspirin to help you with your headache. But whether it takes half an hour and 15 minutes, you don't know how long. You don't know how long it will take the aspirin. You could study this forever. You could become the world's leading expert on how long headaches are after an aspirin's been taken. You probably have like 8 PhDs in aspirin science, all right? And even if you had that level of knowledge, you still wouldn't know for sure how long any given headache would endure after taking an aspirin. You'd have only probabilistic expectations. You might have very low variation. You might have a very precise sense about how long that headache's gonna last, but you don't know for sure. It's an act of hubris to think that you can know for sure. Okay? That is what you might call aleatory uncertainty. It is uncertainty baked into the human experience. There are some things that we just don't get to know for sure. Whether it's quantum mechanics or aspirin headaches. You don't know. Some of these things are just uncertain. All right? That's just life. Other times there's uncertainty because you have an opponent who's got different goals than you. Yeah? So in baseball, let me frame this a little bit. In baseball, there's a pitcher, and the pitcher plays for one team, and their opponent is a hitter for now. And the hitter plays for the other team. And the pitcher wants the hitter to fail, and the hitter wants the pitcher to fail. And the pitcher might have a couple of different ways of throwing the ball, pitching. They might have a couple of different ways of throwing the ball. They have a fast one, they have a slow one that moves a lot, that's called a curveball. They've got a somewhat in between one that moves like laterally, that's called a slider. They might have a super slow one that you don't know what it's gonna do, that's called a knuckleball. Whatever it is, they've got a bunch of different choices that they can make. They have different strategies available to them. A pitcher does. They have different ways that they can pitch the ball. Now the thing with pitchers is they don't want the hitter to know what kind of pitch they're gonna throw. Because if the hitter knew what kind of pitch was coming, then it would be way easier to hit the ball hard. If I knew that you were gonna throw a straight ball that moved fast, I would be ready faster, and I would just say, oh, as soon as I see the ball, just swing in that direction because it's not gonna move a lot. I would know that. Well, you're the pitcher, you don't want me to know that, right? So you're not gonna throw the same pitch every time. You have strategic incentives to apply probabilistic thinking to how you're gonna choose how to throw the ball. So some of the uncertainty of the world is aleatory because you don't get to know, no matter how hard you study, you won't know perfectly how long aspirin affects headache duration. But some of the uncertainty of the world is strategic. Some of the uncertainty in the world is because somebody doesn't want you to know what they're doing for sure. This is gonna come up often when we talked about mixed strategy Nash equilibrium. If one candidate in an election knew what the other one was gonna do perfectly, then it'll be far easier for the first to design a strategy for the campaign. Right? There's all sorts of probabilistic things. I might try to bluff. I might. So, what I mean to say is, this world around us is very uncertain. And you need good techniques for knowing how to survive in that world. And this expected utility thing is actually a pretty big deal because even though expected utility doesn't do a great job of explaining how people actually make choices, because it turns out that a lot of people don't live up to that independence axiom. Back in the B block, we talked about the independence axiom, which seems sensible, but it turns out most people don't live up to that, or people in the lab, you can come up with examples where they don't live up to it. Nevertheless, this is a wonderful normative theory. This is how I would want somebody to make choices under uncertainty. Now, part of that is how I would want a political leader to make choices under uncertainty. I would want them to live up to the independence axiom. I would want them to live up to the continuity axiom. I would want them to have reflexive, complete, and transitive preferences. I, a citizen, hope that my leaders use expected utility because it will maximize the expected value. Okay? But I also care not just about my leaders and whether or not they're doing the right things. I also care about you, my students. I want you, whenever you have an uncertain choice in your life moving forward, to stop, to pause, to say, hey, what are some of these probabilities? Let me just put some guesses on here. Right? If you can make that calculation, then you can make better choices in your own life. There's one of my favorite poker players. Her name is Annie Duke. She has some cool books out now about how to make decision under uncertainty. She's a psychologist. She's also trained as a psychologist. So she's a trained psychologist and a world-class poker player. But a lot of her decisions are not made using psychological theory. A lot of her decisions are made using mathematical rational choice theory like this. And what makes her so great is that she's able to navigate these two worlds so perfectly. Annie Duke is like the coolest, right? And she can help you to make better choices. But a lot of what she talks about is expected utility theory, expected value. So I hope that this is something that resonates with you, and not just in a, oh man, I can see how I could model a country like this. I also want you to be thinking, hey, I should only play a lottery if I have a good sense about what I'm doing and how risk acceptant I would have to be to want to play that lottery. Now, here's something important, and this is the provocative thought with which I wish to end. Never let anybody tell you how much risk you should accept. It's not on me to tell you to never buy a lottery ticket. It's not on me to tell you that. People buy lottery tickets all the time, right? My dad buys lottery tickets all the time. He buys one lottery ticket because he figures if he has a tiny chance of winning, then if he multiplies it by 2, he has double the chance, yeah, but it's still tiny. He kind of views it that if he wins the lottery, it's the Almighty smiling on him, and he doesn't need to buy 2 tickets for that. Right? And I'm not going to begrudge him that. He's a little bit risk acceptant. He likes to live dangerously. He puts salt in his pamplemousse. No, he doesn't. I'm not going to tell him not to buy a lottery ticket unless he's on his last dollar, in which case I'm going to tell him to go to Taco Bell and eat for 7 days. And likewise with you. If you're risk acceptant, make the right choices conditional on your level of risk acceptance. If you're risk neutral, make the best choices that you can, conditional on your risk neutrality. If you're risk averse, make the best choices that you can, conditional on your risk aversion. But don't let anybody tell you about how you feel about those things. Now, this was a big moment for me. When I first started learning these models, I thought that these models were ways to just write fables, and it's true, they are. But you get to be part of the fable too. You are both the writer and the star of your fable. Sorry. There's a lot of dumb choices that you could make. You probably made some. I've made some. We all make dumb choices. And I wish I could tell you that there was an easy class that you could take that would help you to never make another dumb choice, but there isn't one. I wish I could tell you that there was a hard class that you could take, but there isn't one. All that you can do is be deliberate. And to be deliberate, you need to arm yourself with some of these tools, some of which are super simple. If you can make an Excel spreadsheet and you can figure out how much you like risk versus how much you don't like risk, how much you like sure things over potentialities, how much you like big wide distributions where there's some chance of something awesome happening, there's no right way. There is no one right amount of risk acceptance. However, conditional on your amount of risk acceptance, there are good choices that you can make. And I hope that you learn from the fables to come. I hope that you learn what it is to assess somebody's choices. We're going to assess voters' choices, candidates' choices, countries' choices, all fake mathematical ones, but we're going to assess their choices using some of these tools. Okay? And we'll never talk about your fable, but that doesn't mean that you don't have the responsibility to do what's best in your fable too. And so I hope very much that assessing the fake choices by the fake people that live in our fake worlds will help you to make better real choices as a real person that lives in a real world. Thanks for watching.